Okay, well, hi, my name is Skye Fernandez, and I'm currently an undergraduate student at the University of Colorado Boulder. And this summer, I researched apatite, uranium, thorium, helium, thermochronologic investigations of exhumation in the Great Plains and southeastern Colorado and northwestern New Mexico. I would first like to begin my presentation by acknowledging the land my research was studied upon. The University of Colorado Boulder sits upon land within the territories of the people of the mountain, the Ute, Cheyenne, and Arapaho peoples. My research samples were collected in southeastern Colorado and northeastern New Mexico, which sits upon lands within the territories of the Jicarilla Apache, Arapaho, Comanche, and Southern Ute. The Rocky Mountains were uplifted 70 to 45 million years ago, exhumed or eroded, and the rivers carried and buried its own sediment before a later uplift occurred. The reason of this uplift has not yet been discovered, or the extent to what was uplifted. The question we're looking to ask is when the exhumation event happened and how this will shed light to when and why the second post-laramide exhumation occurred. An exhumational or eroding event is different from a surface uplift. Exhumation is an important parameter for understanding tectonic forces acting in mountain belts. With exhumation, it's the displacement of rocks with respect to the surface, and surface uplift is equal to the uplift of the rock minus the exhumation. There's no direct way to measure surface uplift, so we measure exhumation as a proxy tool in order to examine the age of the regional uplift. Apatite helium thermochronology reveals the exhumation age of a rock sample in a rock's time temperature path, also known as thermal cooling, which measures how long it takes the rock to pass through 1.5 to 2 kilometers at a detection temperature of 70 degrees Celsius. Again, we're going to use this exhumation proxy tool to measure the surface uplift of a region, specifically in southeastern Colorado and northeastern New Mexico. From my research, our hypotheses are asking why a difference in exhumation date exists between these two regions and how far the Spanish Peaks younger exhumation event extends across southeastern Colorado and northern New Mexico. And with this, we're going to calculate the first exhumation data of the exhumation extension across this region. Rock sampling. We traveled to southeastern Colorado and northeastern New Mexico to collect 4 rock samples. We collected 3 sedimentary red beds, which are the purple dots, and 1 igneous lamprifer sample, which is the blue dot, because these samples are produced through erosion due to lateral aridity, which falls in our time temperature path of 1.5 to 2 kilometers, which is detected at 70 degrees Celsius. The exhumation date at the Spanish Peaks is 25 to 8 million years old, while the exhumation date of Huerfano Butte is only around 8 million years old. Huerfano Butte is still a part of the same surface uplift event, but has a younger date because it was part of a smaller exhumation episode. Since the rock samples have been exhumed or eroded over time, geologists are able to collect these rocks on the ground instead of having to drill deep into earth for the samples. Oh, I skipped a slide. Apatite helium dating is a widely accepted geochronometer, which measures the amount of helium in an apatite crystal lattice from a depth of 1 to 2.5 kilometers. This closure temperature is at 7 degrees Celsius, which holds helium inside of the grain in order to further measure the exhumation age later on. We use this measuring proxy tool to further understand the surface uplift in southeastern Colorado and northeastern New Mexico. In the figure on the right, you can see that with low temperature thermochronology, we're able to trap and measure the helium, whereas in a higher temperature, the apatite crystal would experience helium leakage that would prevent us from measuring the correct date and provide us with unreliable data. Calculating the exhumation date. When calculating the exhumation date, we want to first look at the uranium-238 to lead-206 decay chain on the right. In this decay chain, uranium-238 is our parent isotope, and helium-4 and lead-206 become the 2 daughter products. When calculating apatite helium dates, we want to flip the equation around, having uranium, thorium, and samarium become our parent isotopes, and helium-4 becoming the daughter product in order to measure the exhumation date in the helium-4 equation that's at the top of the page. Our multi-step rock processing. So During this process, we first collect our rock samples, and then we move to the lab and where we begin to pulverize the rocks. We want to make them as small as 500 microns before we put them through a density separation and electromagnetic separation process. We're going to use the Whiffley board to separate it by density. Then we move to our Franz electromagnetic for magnetic separation. We're going to use a heavy liquid separation step, and we're using lithium metatungstate. And then after that, we're going to centrifuge the samples and then freeze them before separating them one last time and gathering our heavy grains. Whenever we're picking our sample under the microscope, we're looking for non-included grains with a width larger than 80 microns to avoid any helium leakage. When selecting the grains, we're going to select the best grains to date, which means we're looking for grains with a width of equal to or more than 80 microns. This size is important to minimize any helium leakage. On the left, our SF21-3 is a dendrital sedimentary rock and was rounded, which gave us unreliable data later on. The SF21-5 is our igneous lamprosphere that isn't rounded, which gave us much better dates. Mineral inclusions form during the igneous process and can alter the date of our samples. Under the microscope, we pack each grain in niobium tubes and pick the 5 best grains for each samples in order to find non-included grains. This picking and packing process takes the longest and can take up to weeks on end and sometimes even months. The mass spectrometer measures all parent isotopes and daughter products. We're going to dissolve the apatites with no inclusion in nitric acid and dissolve the apatites with inclusion in hydrofluoric acid. The mass spectrometer dissolves apatites with an ultra-high vacuum chamber in nitric acid with a 50-watt diode laser at temperatures going up to 1,000 degrees Celsius for 5 to 10 minutes. Apatites that are dissolved in hydrofluoric acid are dissolved in hydrofluoric acid to avoid any data from other mineral inclusions inside the grain affecting the helium age. And now for our results. At the top of the page, we have the data of our sample grains that were dissolved in nitric acid. On the bottom, we have data of the apatite grains that we dissolved in hydrofluoric acid. The SF21-5 is the igneous lamprosphere that provided the most reliable data. We rejected any grains with an effective uranium of less than 5, which is highlighted in the blue box, because it is a criteria when the helium is low, it is near the detection limit the machine gives us, which becomes unreliable data later on. When looking at our plotting graphs, we compare the date to effective uranium and the date to radius size of the grain. We had one grain that we were going to omit from our SF21-5 mica butte sample because it didn't follow the principles of having high effective uranium equaling an older age. And you can see that right here highlighted in the red. And then with the date versus radius size, it also didn't follow that principle over here of having an older age associated with a larger radius size. We didn't have any ironclad reason at the beginning to throw it out, so we decided to keep it in our graphs, but remove it from the age. Now for our discussion, when we emit the SF21-5 outlier grain, its date changed from 7.8 million years old to 6 million years old. This shows the younger exhumation event that was recorded at the Spanish Peaks and Huerfano Butte regions were able to extend all the way to the eastern Mica Butte. This extends 55 kilometers east, and we really want to extend it in the future with more work. And now for conclusions and future work, we'd like to go back and repick samples LA21-2 and LA20-3 to understand the full extent of this eastern exhumation event. We want to process the 2 buttes over here, which is another lamprosphere sample. And we want to take those 2 good grains that we had highlighted in red before and rerun those as well with other grains from the sample, because we believe it could extend up to 200 kilometers east of the Spanish Peaks. Lastly, for my acknowledgements, I would like to thank Dr. Lon Abbott, Dr. Rebecca Flowers, Dr. James Metcalf, and Barb Peak, my writing mentor, for all of their help, guidance, and understanding throughout this time whenever we had multiple hurdles along the road. I'd also like to thank Sabrina Keynes for her data and letting us build our project around that and to be able to work off of that, which was amazing. And then lastly, I'd like to thank the UNAVCO staff and my future RESESS interns and the Geo Launchpad interns as well for all of their help, and the USIP interns for doing some awesome articles about everyone's projects. And then lastly, any questions?
Great job, Skye. Yes, Yvette, you have questions?
I do. Do you see any, or I don't know if you had a chance to look into that, but do you see any effects of pre-existing structures on your data? Like, can you correlate your data with either Laramide or Precambrian structures?
That is a great question. I'm not actually sure about the answer to that, but I'm really not sure actually now that I think about it. Lon might be great to also ask about it as well because he had a really deep understanding of it as well.
It's probably a whole other can of worms, so that's totally fair that you didn't look into that. Yeah. You're muted, Lon. Lon, you are muted.
Lon, you're muted.
Oh, I am muted. Thank you, Anika. Sorry. Skye's work was on the Great Plains, so those structures are all buried anyway, so we don't really have good control on those.
Okay. So, but you also got into the wet mountains a little bit, like some of it is in the Front Range, I think, or no? I don't know.
The work Sabrina did that Skye was referring to is in the wet mountains. And so we could talk later if you were interested in that, but Sabrina is the one who did that and Skye was trying to take it farther east.
Got it. Thank you.
Great job, Skye. You've got one question from Bara. What was your favorite part of the research process?
I think my favorite part of the research process was probably working with a lot of different people, especially Lon. We had a lot of hurdles throughout the way with all of our grains. We had to run them completely differently than we originally intended on. And every time we encountered some problem, he was just so excited and had a way around it and taught me that, like, no matter what happens with research, you're going to hit roadblocks constantly, but it's going to be okay. And you're still going to gather results and learn a lot from it.
I have a question.
Yeah.
Is there anything you think you would do different, like with your research or all the things that you did this summer?
If there was anything different I could do with my research, I would probably, let me think about that one for a moment. I think with my summer, I would try to spend more time in person at the lab. Being in Boulder, I really enjoyed that, and I really missed going remote for part of it. And I really liked the lab experience. So, but that's kind of an uncontrollable. So I don't think there's anything in my control that I would change looking back.
That's great. Yeah, you've overcome a lot. So that was awesome.